Okay, let us start our lectures again. Well, before the break, we finished all our lecture notes for CMOS method. You have learned how to analyze a charge beam frame using CMOS method, which is a matrix approach. Any questions? 冇問題。Just remind you that we have one assignment 1. In this assignment, we have 3 questions. The first one is for truss structures. This question, truss is not difficult, but these structures, we need to consider quite a lot of external effects. We have applied loadings, inclined force. We have to resolve the inclined force into horizontal and vertical loadings. And then we have temperature change, we have fabrication error, we have support settlement. So in question 1, you need to consider 4 external effects: force, temperature, fabrication error, and settlement. We have totally 4 effects in question 1. You can follow the classical procedure, formulate the equation, solve for displacement, solve for reaction, solve for member action force. Question 1, you know how to do it at this moment. Question 2, beam. You also know how to analyze beam using CMOS method. Here I give you 1 tip. The tip is that you can divide the beam into 3 elements. Element 1, element 2, element 3. And then you can solve it using 3 elements. Solve for the displacement, solve for the reaction, and then draw the shear and moment diagrams. Today, after the lectures, you should know how to complete question 3 as well. Question 3 is a plane frame under distributed force and under horizontal force. You're asked to use CMOS method to find out the displacement again, find out the reactions, and draw the shear moment actual force diagram. The tip is that you may use Excel to solve this problem because you will find that the problem size is quite big. You may use Excel to use matrix inverse to find out the unknown displacements. So now you can complete the whole assignment 1. All the things has been covered. Okay, any questions? Any questions you want to ask me? 有冇問題你想問我？ If no questions, then I prepared 2 tutorial examples for you regarding to CMOS method again, frame structures. So perhaps this is really the last part of CMOS method. We will finish our tutorial 3 examples right now. And then after that, I will close CMOS method. And then we will enter another new big chapter, structural dynamics. Let us finish the remaining 2 examples. Let me share the screen with you. This is really the last part of CMOS method. Tutorial 3 for our frame structures. We have only 1 objective in these tutorial sections, which is to demonstrate the use of CMOS method for plane frame analysis. There are 2 simple examples help you to refresh your memory about how to play with CMOS method for frame structures. Let's see how to deal with the problems. Suppose we have simple frame structures. This one is you know the scope of these structures. Example 1 is within the scope of our module. During the quiz examinations, we have 3 unknown displacement, We have horizontal and vertical frame members. We have UDL, these kind of things. What we are going to do in this example, you're asked to determine the displacement at node 2 and find out the reaction as a pole. Try to draw the shear and moment diagrams. 3 tasks, just like what I asked you in the assignment. Displacement, reactions, and also and the shear and moment diagrams. You know the material properties E, you know R, you know A. This structure is under only uniformly distributed load on the top. You know the length. In this problem, I discretize the structures for you. We have element 1, element 2. Okay, I give you around 2 minutes. You may think about the overall procedures, what you have to do. After 2 minutes, I will go through the questions with you. Okay, you may think about what you should do in step 1, how to discretize the structures, where are the known displacement, where are the unknown displacement, and then you can try to think about which series matrix you should use for element 1, element 2. At the same time, you may try to take a look of the pattern of the force displacement relationship. Try to identify which part is useful, which part is useless in the series matrix. I give you some time to think about the solutions, and then we will go through together. Ready? Example 1. 2 members, 1 and 2. Suppose we are going to solve this problem using series method. Then what you have to do firstly, discretize structures into different members. Here we can see that we have element 1, horizontal member, we have element 2, vertical member. You can at the same time assign the code number for each node. Horizontal, vertical, rotation, horizontal, vertical, rotations. You can also assign the member orientation because I did not give you the member orientations in the problems. Horizontal member, turn from left to right. Vertical member, turn from the top to bottom. The member orientation is also arbitrary, right? In tutorial 1, if you still remember, in tutorial 1, I showed you the effect. What happens if you change member orientation? What happens if you change the code number order? They will not affect the final answer. So you can feel free to assign the member orientation and code number. Why I arrange the member orientation in this manner? Because I can construct the matrix easily. In the notes, I give you the simplified matrix for these 2 directions, right? That's why I pick these 2 directions. I don't want to use the complicated matrix. So next you can start to assign code number. You can follow textbook method, or you may assign the code number arbitrarily. If you want to follow the textbook method, then you have to determine where you have unknown displacement. As usual, if you see a fixed n, you should feel happy because it's fixed n. we have no movement, 0, 0, 0. At the other fixed end, we have no movement, no rotations. Free end is also easy. Free ends mean free to move, free to rotate. So you will probably see 3 question marks here. We have 6 zeros. We have 3 question marks. You can start to assign code number at node 2 first, and then assign the code number for the remaining arrows. I think in the notes we have a similar example, but we change the boundary condition a little bit, and then we change the loading to UDL. That's why you can automatically construct this code number diagram. 1, 2, 3 used to denote the positions with unknown displacement. The other the known displacement position fixed end. We have 2 fixed end, 6, 0 correspond to code number 4 to 9. You should feel happy because there are many 0 displacement. That means our CMOS matrix, only a small part are useful. QK is a 0 vector, 0 force vector, because from the picture, we don't have any applied loading. We don't have any joint load. We don't have loading applied at the joint. You cannot see concentrated force. You cannot see concentrated force. You cannot see concentrated moment applied at the nodes. So from this picture, we have no nodal force. QK is 0. UDL, you have to change UDL to the fixed end force and fixed end moment using the diagram that I provided in topic 2. Find out the shear, find out the moment, and then put it into the Q0 vector. Q0 vector. So you have to do one extra step. Convert the UDL to fixed end force, fixed end moment, and put it into the Q0 vector. Here I show you the code number diagram, member orientation in purple color. We know all the things. New things. Symbolic equations. In step 1, actually you can put down this force displacement equation, even though we have no idea what happened in the matrix. What about these equations? I just put down the force vector, Q, and substitute QK into this force vector. Similarly, I construct our displacement vector, substitute dk into this vector, plus fixed end force. For CMOS matrix, we have no idea what it is, right? Because we have not yet construct the element matrix. But from these symbolic equations, you can see that, from this equation, I can see that column 4, column 5, column 6, column 7, column 8, column 9, they always multiplied by 0. So these 6 columns, you don't need to know their numbers because they are useless, they're irrelevant to your calculations. So in step 1, you can immediately identify which part is useful in your matrix. So when you construct your element matrix, when you do the matrix additions, you just need to pay great attention to row 1, row 2, row 3. Column 1, column 2, column 3, because they will really affect your calculations. For the remaining part, well, you may put them symbolically, call that K1, K12, K22, something like that. So this is what I mean. You can immediately observe which part is useful at the beginning, if you're familiar with the force displacement relationship. It may somehow save you some time, I think. Next, you have to obtain the structure CMOS matrix. I copied the part of the notes to the solution here. For horizontal member pointing from left to right, you can find out the matrix from the initial notes. For vertical member point from top to bottom, you can also find out the corresponding element matrix. Just find out EAL, 12 Albert L creep, and then substitute their values back to these 2 matrices. You know the length, you know E, you know A, you know I. So everything within the matrix are well divided. On the question page, I tells you E, A, L, so you can use them directly. Because these structures, we have same length for member 1 and member 2. When you go into the problem, you can see that here, they are all 4 meters, 4 meters, 4 meters. So the most easiest way in this problem is to firstly find out the common factor. Find out the common factor, EA over L, find out 12 E over cube, blah, blah. These kind of values can be applied for both members in this problem. So that's why I firstly find out these factors, EL, 12 EI over L cube, 6 E over L squared, find out their values. Be careful about the unit conversions. You have to keep all the units consistent to each other. Here, I use Kn for force, I use meter for length-related parameters. But if you like, you may change to the other units. You may use mm or you may use Newton in your calculation. Just make sure that everything consistent. Here, I use Kn and meter in my calculations. I calculate these few factors and substitute back to the horizontal matrix. This one. Nx, Ny, Nz. Remember the corresponding directions. What is Nx? This is the orientation of element 1, horizontal member, points from left to right. This tells you where is not N, where is not F. The arrows point to not F, the starting point is not N, so you can see clearly that Nx represents code number 4, Ny represents code number 5, and then 6. 4, 5, 6, 1, 2, 3. This is the code number order that we have. And then answer one questions. Which plot is useful in this element matrix? From the previous page, I just showed you here, right? Row 1, row 2, row 3 are useful. Sorry, I should be column 1, column 2, column 3. I speak out the wrong terms. Column 1, column 2, column 3 are useful according to these observations. So in element level, which plot are useful? Which plot are useful? Column 1, column 2, column 3. It seems that this plot will affect our calculation a lot. So you have to pay great attention for this portion because it will only affect your calculation, right? Column 1, column 2, column 3. At the same time, you have to find out the fixed end force. Because element 1, you can see that element 1 is under UDL, 40 kilonewton meter. We have to use our fixed end force diagram. Did I show you the picture? No, it doesn't matter. Let me erase the picture a little bit here. You can treat this as something like a fixed end beam. Find out the corresponding fixed end force and fixed end moment. In topic 2, I showed you 2 pictures. One is for UDL, the other one is for point load at midspan. Right? I only assess you these 2 scenarios for intermediate loading. The fixed end force is equal to W L over 2. While the moment is equal to W L squared over 12. If you use this several times, I believe that you can memorize the values. The force, WL over 2, which is equal to 80. The moment, WL over 12, which is equal to 53.3 kilonewton meter. You put them in a vector form, Q10. Remember that when you express them in a vector form, you need to provide all components, Nx, Ny, Nz, and then Fx, Fy, Fz. Nz, Fx, Fy, Fz. The arrangement is actually the same as what we did for element matrix. nx, ny, nz, and so on. Then you just go back to this force diagram to see what is the force along nx, what is the force along ny, what is the moment along nz, and so on. Nx, I just erase the symbol. Nx means the horizontal component, and not n. From this fixed end force diagram, you can see that we do not have any horizontal force. So Nx component is equal to 0. Ny means the vertical component, which is the vertical force, vertical fixed end force. It is equal to 80, and then moment, 53.3. Positive, because this moment is anti-clockwise. On the other side, not F. Not F, we have no horizontal force. We have one vertical force, positive. And then finally, the moment is negative because the moment is clockwise. On the right-hand side, clockwise moment, this one. Clockwise moment is negative according to our sign conventions. So we have this fixed end force right here, Q0. It's involved code number 1, 2, 3, 4, 5, 6. It's missing 3 code numbers, right? 7, 8, 9. If you like, you may add code number 7, 8, 9 into this vector and then fill them with 0. Element 2, you can see that I just copy and paste. I copy this set values to this page because they have same length, same E, same I, same A. But you use different matrix. We use the matrix for vertical member pointing from top to bottom. Element 2, there is no any intermediate loading. So Q0, Q to 0, maybe I call it this way. Q to 0 is a 0 force vector, no intermediate loading. You get annoyed. Similarly, you can take a look to see which part is useful. Column 1, column 2, column 3 are useful, right? According to our discussion before. So this part, you have to pay great attention to their numbers because they will really affect your calculations. Then you can try your best to assemble K1 and K2 to obtain our element, to obtain our structure sequence matrix by K. Subdivide by K into 4 parts. Right. Then you can see the expression again. Column 4, column 5, column 4, column 5, column 6, up to column 9, they always multiplied by 0. So that's why they are redundant, they are useless. When you do the matrix assemble, actually you can ignore their property because they will not affect your calculations. But in the notes, I present everything to you so that you may practice yourself if you have time. Just need to pay great attention to column 1, column 2, column 3, these 3 columns. Plus fixed end force vector Q0. As usual, solve the equation on the top to find out unknown displacement. Solve for the first 3 rows to find out unknown displacement, D1, D2, D3. And then use the bottom 6 equations to find out unknown reactions. Very, very classical procedures. Row 1, row 2, row 3. You may solve for 3 simultaneous equations if you like, or you may use matrix inverse. Depends on which skills you are more familiar with. I think this one, if you solve for 3 simultaneous equations, is not that difficult because there are some 0. So equation 1, you only see D1 and D3, right? Because D2 multiplied by 0. Equation 2, you will see D2, D3, but no D1. So you can set a relationship between D1, D3. You can set a relationship between D2, D3, and substitute them back to the last equation. 3 equations, 3 unknowns. You can solve for all unknowns all unknown displacement easily. D1, D2, D3. Or if you have Excel, you may use Excel to find out matrix inverse and then solve it. Ratio multiplications. Give you the displacements, d1, d2, and rotation, d3. We use radian for rotations. Very classical examples. If you know unknown displacement, then the next part you have to use the bottom equations, bottom 6 equations to find out unknown reactions. Here, you have to use the bottom 6 equations to find out Q4, Q5, Q6 up to Q9. Because in this question, you are asked to find out also the reactions. This row times this column plus the additional force vector give you Q4. And then the fifth row times displacement vector plus the fxn force vector also give you Q5, and so on. You may do this row by row if you like. Or you can use matrix operations. K21 times du plus Qu, part of Qu. K21 du, part of Qu. You may use matrix operations if you like. The first row times displacement vector plus the first element give you the force, Q4. And then the second row times displacement vector again plus this element, Ht, give you Q5. You can do this row by row. Then you can get Q4 up to Q9. Q4, positive. Where is Q4? Q4 means the force along direction 4. Where is direction 4? You have to go back to the code number diagrams. Here. 4, 5, 6, 7, 8, 9. From here, you can see their meanings. Q4 means the reaction, the horizontal reactions for this fixed end. Q5 means the vertical reactions at the fixed end, and then the reaction moments. Q4 plus mean is pointing to the right hand side, right here. Q5 positive. Positive mean is pointing upward. 90.8. Moment Q6 positive. That means the moment is anti-clockwise moment. Anti-clockwise moment here. So from the calculation, you can see the direction, you can see the magnitude, and yeah, you know everything. Q7. Q7 is here, right? At the bottom. At the bottom. The value is negative. A negative mean is pointing to the left. This one. Maybe I change the color a little bit. Maybe I use blue, I use green. Q7 is negative values. Negative value is pointing to the left hand side. This one. So be careful about the positive and negative design. It shows you the orientations. Q8 means the vertical component. Positive means pointing upward. Going up. The last one indicates moment at the fixed end. Positive. Positive means it is anti-clockwise moment. Anti-clockwise moment. So you can convert the answer in better form back to the picture. Becomes something like a force diagram. From the force diagram, you believe that you can draw the shear and moment diagrams immediately. From the force diagrams, You can draw these kind of pictures. Actual force diagram easy, right? Because you can see the actual force directly. You can see the actual force directly from the picture. Element 1 under compression 9.5, element 2 under compression 69.2. I take compression as negative, so you can see that the actual force diagram involves only negative values. For the shear diagram, element 1, you have upward force, so you will firstly see upward jump, right? And then you have UDL, then probably you will see a slope, negative slope, up to here in your shear force diagrams. And then go to element 2, we have a force here, we have a shear force going to the right hand side, and then along here we have no force. No force means you have a horizontal line, and then finally close it. All right. If you have the shear diagram, you can convert them to moment diagrams using graphical relationship, or you can use the other approach that you're familiar with. I show you one dashed line here. The dashed line shows you that according to the relationship, V equal to dm dx, the slope in the moment diagrams is equal to the value of the shear force at that point. So from the picture, you can see that the extreme positions, the maximum moment, the slope is equal to 0. So this maximum moment should appear at the position with 0 shear force. Extreme positions, right? We learned this from calculus. If you want to find out maximum or minimum, then you can find out the slope and set it equal to 0. This kind of skill can help you to sketch the shear moment diagram immediately. This is also required in these questions because we are asked you to find out displacement, reactions, and draw the diagrams. Okay, example 1, a classical example. This kind of questions will be assessed in the quiz or examination, so make sure that you know how to deal with them. In the exam, I mentioned that in the exam, because of the time constraint, I cannot give you too many unknown displacement. I can only give you at most 3 unknown displacement. So this one is within the scope of the exam. You have 3 unknown displacements. And also for frame structures, I only assess you horizontal or vertical members. So the arrangement is also within the scope. So make sure that you understand how to play with this example 1. Okay. The solution, I think, is also clear. Tutorial 2, example. Now, this example I prepared for you to complete the assignment. Complete your assignment 1, question 3. For examination, I can't assess you this portal frame because too many unknown displacement. You will know very soon. Or maybe you know the number of unknown displacement immediately. How many? You have 4 joints, you have 2 fixed support. You have 4 joints, each joint you have 3 degrees of freedom. So in total, you have 12 degrees of freedom. Among these 12 degrees of freedom, you have 2 fixed support. 2 fixed supports mean you know 6 components. You have 6 0. You have 6 0 mean you have 6 unknown displacement. You have 6 question marks. So immediately you can see that we have 6 unknown displacement, bigger than the thing that we can handle in the quiz and examinations. But in assignment, I can assess you a relatively big scale problem because you're allowed to use Excel to do the calculations, matrix inverse or matrix multiplications. I've already demonstrated how to use Excel to inverse matrix and do the multiplications. Right, but to complete the story, I think it's good to have one example to illustrate how to play with a portal frame. Normally, a frame is something like this, right? A portal frame with 2 columns, 1 beam. So let's have a look quickly to see how to play with these examples. I think I just copied the questions from example 1. Find out the displacement, find out the reaction, find out the moment, and shear force diagram. I just copied these descriptions from the previous example, and then I changed the picture. What about these structures? These structures, we have three members, vertical, horizontal, and then vertical members. There are three external effects. We have one horizontal force acting at the middle of element 1. We have another force acting at the middle of element 2. We have one concentrated moment acting at joint 3. So in these questions, you have to handle concentrated moment. You have to handle two intermediate loadings on element 1, on element 2. We have learned how to handle intermediate loading, right? You convert them to fixed end force and fixed end moment, and then put it along Q0. M is concentrated moment applied exactly at the node. So mathematically, you can put it into the so-called QK vector. QK vector. And in these questions, you know E, you know A, you know I. So you can find out the elements of a matrix, K1, K2, K3. The procedure is classical, but it involves quite a lot of calculations. Firstly, you can set up the Coulomb diagrams. We have totally 12 errors. I just showed you. 1, 2, 3, 4, 5, 6. Each node will have 3 degrees of freedom. Again, we take counterclockwise as positive. We take counterclockwise as positive. We have totally 12 errors. You have to assign code number 1, 2, 3, 4 up to number 12. You may follow the textbook method, assign code number from positions with unknown displacement first, and then assign the remaining positions. So you can assign your code number from node 2 and node 3, because they are free end, right? Free to move, and then assign the fixed end. Assign the top first. Assign the code number at the top first. 1, 2, 3, 4, 5, 6. And then the remaining 6 numbers you can assign at the fixed end, according to the textbook suggestions. Assign code number from position with unknown displacements. At the same time, you can put down the member orientation. Member orientation in purple color. Go up, go horizontal, and go downward. If we arrange the member orientation along the same directions, here, 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 just like a straight line, I think it will be more easy for you to draw the shear and moment diagram. Just like a continuous beam, something like that. So this is the Coulomb diagram we would like to follow. You may also use similar idea in your assignment 1 question 3. And then you can put down the known force, known displacement. Normally I put down known displacement first because I think it's relatively easy to obtain known displacement because they're talking about the support conditions. We have 2 fixed ends correspond to Coulomb 7 to Coulomb 12. So we have totally 60. D7 to D12 are 0. QK should involve the remaining number 1 to 6. Then you go back to the corresponding directions 1, 2, 3 to see if there is any concentrated force or concentrated moment applied at those positions. Direction 1 here. Direction 1, 2, 3, 4, 5, 6. Then you go back to see if there are any force or moment along these 6 directions. There's no force, no moment. So Q1, Q2, Q3 should be 0. There's no horizontal force, no vertical force, but there is one moment. There's one moment at this node 3. The moment is a clockwise moment. Clockwise moment. Clockwise means Q6 is equal to negative 1,000 minus 1,000. Direction 6. We have a negative concentrated moment minus 1,000. Be careful about the directions. Clockwise means negative, according to our sign conventions. Q1 to Q5, 0. Q6 minus 1,000. And this is the known force and known displacement. Then what about the 2 concentrated forces acting at the midspan of member 1 and member 2? you have to find out their fixed and false. You can treat this as something like a fixed and member. And then find out the false, find out the moment, fixed and false, fixed and moment. Put it into the so-called Q0 vector according to their code number. Just do this twice because we have two intermediate loading. Do this step twice. I go through this quickly because no new things. Just using the matrix. Not much things to further discuss about the matrix. K1, you can use. I give you one matrix for a vertical member pointing upward. You may go back to, I think it's page 16. I show you one matrix for flat member pointing upward. You may use that matrix to find out K1. Code number order 10, 11, 12, 1, 2, 3. Code number. We start from node n. Node n, nx, 10, ny, 11, and z, 12. Nx, ny, and z. This is the common order we follow. And then fx, fy, fz. 10, 11, 12, 1, 2, 3. It helps you to construct the structure sequence matrix later. Element 1. Element 1 is under one concentrated force at this band. This one. Element 1, there is one concentrated force at this band. We have to convert this concentrated force back to fixed end force and fixed end moment. Here I want to discuss a little bit because this member is a vertical member. In the notes, we just consider horizontal members under concentrated force. Then what happens for vertical member? When you calculate the fixed end force and fixed end moment, you can treat this member as something like a fixed end member, fixed at the top, fixed at the bottom. And then you can put down the fixed end force, fixed end moment in this manner. And the notes, I give you one picture like this. Horizontal member under concentrated force at the middle. In the notes, I give you this picture. You just rotate this picture by 90 degrees. Then it becomes the picture on the bottom right hand corner. Just rotate the picture by 90 degrees. And we have force, we have moment, force, moment. Rotate this picture by 90 degrees. It becomes the picture on the bottom right hand corner. And then find out their values. Find out the fixed end force, find out the fixed end moment. Fixed end force is equal to P over L. P over 2. P is 1000. So the force is equal to 500 kilonewtons. Fixed end moment. PL over 8. PL over 8 is the fixed end moment. P over 8. We know the force, we know the length. The length is 5 meters long. Over 8. Fixed end moment. This is the fixed end moment force and fixed end force and fixed end moment. You have to finally convert them back to our vector form in element level. The vector form in element level, we follow the order nx, ny, nz, fx, fy, fz. When you consider vertical member, here you have to pay great attention because the arrangement will be slightly different from horizontal member. Here you can see that we start from nx direction. Where is nx? Nx is here. Nx is the horizontal directions at node n, at the bottom node. Okay, Nx. When you go back to the fixed end force diagram on the right hand side, here is node n, Nx means the horizontal directions. And you can see that we have a force, but the force is pointing to the left, which means it is a negative number, minus 500. The force is pointing to the left. Be careful about the position, be careful about the sign. Ny. Ny means the vertical component. Vertical component, we have nothing. We have no vertical component right here. Because there is no actual effect. So 0. 0. And then the last, not the last item, the third item, NZ. NZ represents the rotation degrees of freedom, which is here. When you go to the picture, we have a moment at the bottom. The moment is anti-clockwise. The value is 625. So positive. Anti-clockwise moment, positive. So you can use this arrangement, convert the fixed and force diagram back to a vector form. Just put down the picture clearly, put down where is not N, not F, put down where is NX, NY, NZ. Then I believe that everyone can convert them back to vector form. Fx. F is the upper node. Fx means the horizontal component. From this picture, we can see horizontal force, but the force again is pointing to the left. So it's negative, pointing to the left. Fy, Fy means the vertical component, but from the picture, we don't have any vertical component, so 0. Finally, the moment at the top, the moment at node F. It is a clockwise moment. Clockwise means negative. So we have a minus value. So when you do the conversion, be careful about the sign, be careful about the positions. For vertical member, we can use the same idea to calculate the Q0 ratio. It involves code number 1, 2, 3, 10, 11, 12. This may help you to solve the assignment 1 question 3 problems. Because it seems that there is also horizontal force. Member 2. Member 2 is a classical member, horizontal, under intermediate loading. This one I think is more straightforward because it's just like a beam. Just like a beam. This one you calculate the element Sylvus matrix, K2, using the given Sylvus matrix, and then calculate the fixed end force, fixed end moment, convert them back to a vector form. This one is quite similar to what we did for beam analysis, and also similar to the example in our lecture notes. NX. NX means not N, X direction. X direction, we have nothing right from the picture. NY, we have a vertical component, 250. And then NZ means the moment. NX, NY, NZ, and then Fx, Fy, Fz. You can convert them back to a vector form. 0, 250, 250, 0, 250, minus 250. Minus 250 at the bottom, because it is a clockwise moment. Fz component. Element 2. Only element 3. Element 3 we have no intermediate loading. So for element 3, Q0 is a 0 vector. You just need to construct the Sylvus matrix.
街市文化為主題。
I put the matrix in Excel, K1, K2, K3, and then I do a simple matrix addition in Excel. You know, matrix support addition, subtraction, and multiplication. So you can, if you don't want to do yourself, maybe you can put all the things in Excel and then directly put them together. It becomes our structured Sylvus matrix. Which part is useful? You can cut the matrix into 4 regions. Starting from column 7, they always multiply by 0. So the second half are redundant.
展現出當時人民的生活習慣， 以及
try to practice how to assemble matrix. Maybe you can practice using some
文化
more easy example, like example 1 or the example in the notes, lecture notes. This one is quite comprehensive. I suggest you may use Excel to do the calculations. We have two Q0, one for element 1, the other one is for element 2. Okay. You may firstly enlarge the vector to a 12 by 1 vector with ascending order in code number. So it helps you to see which
部
part
分攤檔
are
會
along the same code number,
保
same
留
positions.
原貌，
Add up their values if they are along the same positions.
再
Q3, actually you can ignore Q3 because Q3 is 0. But to
重
complete the
新
story,
翻
I
修
also
後，
put it here
務求
because
呈
we have
現
3 members.
最
Just add them up
原
row
汁
by
原
row.
味的
It
樣貌。
becomes your final Q0 vector. Just simple additions. Then, wow, you can get this full equations. Q equal to KD plus Q0. In assignment 1, question 3, you need to formulate these kind of things, a big matrix equations, and then solve for unknown displacement, du. After that, solve for unknown reactions, QU. Okay. Here you can use Excel matrix inverse Q1, these equations. Q inverse Q1 times QK minus Q0.
另一部分
You can move Q0
的攤
to
位
the left-hand side of the equation. It becomes QK minus Q0 equal to K11 du, and then multiply the whole equation by K11 inverse. That becomes these equations. You can solve it using Excel. You can use a command m inverse to find out K1 inverse. You can use a command mmult, matrix multiplication, to multiply two matrices together. Then you can successfully get this displacement vector. In your assignment solution, you may express in similar manner. Just tell me what is QK, Q1, Q0, and then you can put down the equation, and yeah, you can say that by Excel, you get the solution like this. Same for reactions. You can use the bottom part of the matrix equations to get unknown reactions. Finally, put them back to the picture to see force diagram. You know the reactions, you know the applied loadings, you know the reactions on the right. Okay, you can convert the number, say for example Q7, Q8, Q9 back to the support positions. I think we just explained in example 1. Where is 7? You need to go back to the code number diagram to see where is direction 7. Seven represent the node on the right. 7, 8, 9, 10, 11, 12. 7. So Q7. Erase the text first. Q7. Q7 represent the component at node 4 along the horizontal directions. The force is negative. Negative force means it's pointing to the left. Q7, pointing horizontally to the left. Q8 represents the force along direction 8, which is the vertical direction, and node 4. Positive, so the force is going up. And then Q9 represents the moment, and it is a clockwise moment. It is a positive moment. Positive moment means it is anti-clockwise moment. So after finish the calculations, you have to know how to convert them back to the picture. Pointing to the left, pointing to the right, point up, point down, clockwise, anti-clockwise. And then Q10, 10 is the order fixed n. Here. Q10, Q11. 11 is pointing direct right here. And then Q12. Q12 is a big moment at the support. So you can now convert them back to the force diagram. From this diagram, you can try your best to draw the shear, draw the moment, draw the actual force diagrams using our structure analysis skills. You can use graphical method, or you may use method of section, or you may use classical method, finding the shear function, moment function, etc. There are many skills to draw the diagrams. These questions mainly used to help you to find out to solve the assignment 1 questions. For exam, I can't assess you this scale because it's too big, too large. You don't have time to finish the questions. So this one is just help you to find out the answer for assignment 1, question 3. Okay, these are the things I want to share with you in these tutorial sections. Let's see if you have any problems. You may ask me in Cantonese or you may ask me in English.
展示街市原貌，甚至整可以透過虛擬實境帶上特定裝置體驗以往街市，
有冇問題？
親身體驗往日街市景色。
Anyway, maybe we go short break again, our second break. During the break, you may also have a look of the notes to see if there's any questions. I think we may have a short break. Thank you for your response. If no questions, maybe we can take a short break, 5 minutes break.
加上互動形式。問答攤位，透過以
Okay, let us go to the last part of these lectures.
透過參與
Right now, we have finished topic 1, topic 2, and topic 3. We successfully finished all the contents within
了解香港
A little bit recap the contents. For topic 1, I give you the notes, I give you the tutorial notes. I also upload some supplementary examples. Trust. And also we have supplementary example for BIM.
以及
So if you want to do more
該建
practice,
築物的
maybe you can have a look at these supplementary examples for your self-practice. And we have one notes for Excel approach. If you want to use Excel, maybe you can have a look. Today we finished here, we finished our frame, we finished our tutorial 3. So we finished all the contents for Civil Method. Last time tutorial 2, I found that there is something wrong about the videos. I think there's something wrong about the display. So I upload the videos that I prepared in last year. You may have a look to see if any questions. If you don't understand, I'm feel free to make a class for you. Okay. If you don't understand the content within this tutorial 2, I can make additional class for you to review to go through the question again. It just takes you around 1 hour. So feel free to inform me if you really need this kind of supplementary arrangement. Because when I go back to see the video, I found that there's something wrong about the display. The video has voice but no picture. I don't know why. But anyway, yeah, this is arrangement. Trust, BIM, frame. I can use one simple slide to conclude the contents. This is one slide obtained from topic 2, BIM analysis. Right, you can see that when you want to use Civil Method, the basic procedures are basically the same. Firstly, you discretize the structures into different elements, assign degrees of freedom, etc. And then you can construct the element matrix, put them together to form the structure Civil matrix. After that, you can consolidate all the known information. Find out Q, K, D. Sometimes you have to add one additional force vector, Q0, on the right. And then solve it. Solve for DU, always solve for unknown displacement first, and then unknown reactions. These are the overall procedures for Civil Method, applicable for BIM, for truss, for frame. Okay, any questions regarding to Civil Method? I think Civil Method maybe the most difficult things is about mathematics, how to do matrix addition, multiplication, matrix inverse. In terms of the structural concept, I think it's not that difficult for Civil Method. You just need to remember some sign conventions, what is positive, what is negative, and you also need to know how to assign code number, how to assign degrees of freedom. I think these are the only new things in Civil Method. The other thing is just related to how to solve the matrix equations. No questions. If there is no questions, then maybe we can we can go to another chapter, structural dynamics. According to the arrangement in Moodle, we are now going to topic 4. We will firstly talk about the formulation first, how to formulate the equation for dynamic system. Topic 4 mainly focus on formulation. And then topic 5, topic 6, topic 7, topic 8, we try to focus on each different scenario to find out the behavior. Firstly, we consider free variation in topic 5, and then we consider forced derivation in topic 6. There are some specific topics to focus on a system under different kinds of dynamic loadings. And then we will go to a more complicated topic in the future. We call the MDOF, multiple degree of freedom system. So let's go to topic 4. Structural dynamics. Topic 4. This is a new chapter, structural dynamics. Now you can put down matrix. You can focus on dynamics at this moment, although you will see matrix again in the future. But at least in topic 4, there is no matrix right here. Topic 4, introduction to structural dynamics. In this topic, we are going to focus on a simple system. We call it SDOF system. You will learn what is the full form of SDOF. And then we will set up the equations, the governing equations for a dynamic system. We call it equation of motion. This is the arrangement of this small topic, topic 4. Firstly, we will talk about equation of motion, single degree of freedom system, and then we'll talk about how to convert a real problem to something that we can handle, structural idealizations. We talk about influence of gravitational force, and then finally we talk about support movement. Support movement is related to something like earthquake. We will firstly talk about the basic formulation, and then consider some additional effect due to gravity due to support movement, etc. Firstly, talk about those basic background. I think it's good to start from static again. Static, so far we learned many things about static analysis. So I think it's good to start from here and then move to dynamics. So what is static? Static means something that does not move, right? Does not change with time, simply speaking. The force and moment, or the displacement, they will not change when time goes on. The values are something like constant, you can say in this way, do not vary with time. For this case, we may call this a static problem. In the past, we have considered how to analyze a truss bridge under concentrated force. The force is constant. P1, P2, P3, they are constant apart on the structures. So in this case, you can find out the diffraction, you can find out the internal forces, they are also constant. They does not change with time. For frame, you can find out the moment, you can find out the shear force, you can find out actual force. Similarly, in the past, assume that the force are constant. So you can find out the unique solutions at different joints. How to find out their values? In the past, we used equilibrium conditions. Equilibrium condition tell us this equation: summation force equal to 0. When you sum out external force and internal force, it should give you 0. That means equilibrium. That's the conditions. Then what about dynamics? Dynamics, simply speaking, you can think about the scenario image. Summation force is not equal to 0. When you add up all the force, in case if it's not equal to 0, then what will happen? In our high school physics, we have learned what happened in this scenario. In the past, we start from a car under applied loadings, right? Net force. The car will accelerate when you apply a force to push the car. We use what equation to describe this problem? We use Newton's second law. Newton's second law actually tells us this scenario when add up all the force which is not equal to 0. Summation force not equal to 0. equal to what? Equal to m times a. For dynamic problem, the equation can be derived using Newton's second law. Summation of force is not equal to 0, but equal to mass of the object times the corresponding acceleration, ma. A very famous law to govern dynamic problems. So starting from this topic 4, we need to use this Newton's second law to firstly formulate our problem and then solve it. This topic 4, we mainly focus on formulation. Next time, topic 5, we will start to talk about how to find out the solution. For a dynamic problem, the force, displacement, or the other structural response, they will change with time varying function. It may change the relative, change the direction, or change the positions. Everything changes with time. That's why we call it dynamics. Some description, mass is the inertia of one object, mass, kg or tons, depends on what unit you use. A stands for acceleration, accelerations. What is the relationship between acceleration and displacement? We use A for acceleration, we use displacement, we use U to denote displacements. According to our high school physics, when you differentiate displacement with respect to time twice, it will give you acceleration. So symbolically, d square u dt squared is equal to acceleration. But for expressions, we don't want to put down this d something dt too many times. So there's one short form. The short form is dot. When you put one dot on the top, which means differentiate this with respect to time. Two dot mean differentiate twice. Three dot mean, yeah, so 3 times. We use u dot, u double dot to denote differentiations with respect to time. Okay, there's some description about the symbol. Now, one thing, when you read the textbook, some textbook would like to use x to denote displacement, not u. In the notes, I think I mainly use u to denote displacement, but sometimes I may use x. Anyway, they are talking about displacement. A for acceleration, you may use A for acceleration, or you may use u double dot. Depends on which one you are more familiar with. Normally, I use u double dot to describe accelerations. There are some basic characteristics I would like to firstly talk about, let you know the difference between static and dynamics. The first one we have already go through. Dynamic problem, all the properties are time varying in nature. What is the meaning of time varying in nature? For static problem, when you apply a constant force on the top of structures, you can find out one unique solution. Right? 10 mm or 100 mm, you can find out one single unique solution. But for a dynamic problem, the force changes with time. Mathematically, you can call this a function of time. This bracket means the force is a function of time, depends on time. One classical example is, say for example, the force can be a psi function, a constant, maybe I call this A. I use some simple terms at the beginning. A, which is a constant, time maybe a psi function. A force can be a sinusoidal force. When you plot this graph, it becomes something like this, a psi curve. A force can oscillate using a psi function. When you consider a loading duty machine, when the machine operates, a motor rotates, it will generate this kind of sinusoidal force, making the structure oscillate up and down. So this is a force varying with time. One classical example. The force can be arbitrary, just like the force due to wind or due to earthquake. It can be arbitrary, so it's not necessary to be a psi function. So PT is a very general term, which means that the force changes with time. It can be any shape, sine, cosine, tangent, or complex random shapes. Simply speaking, PT. When you apply a dynamic force on a structure, The displacement, very complicated. And firstly, you can see that the value is not a single value. The value changes with time. At different time instant, you will get different numbers. Sometimes positive, sometimes big number, sometimes negative. For some simple scenario, you can find out the displacement function. The displacement can be described using some simple function. Again, sine, cosine, this kind of things. For some simple case, you can do so. From some complicated scenario, like for a structures under earthquake. Earthquake is also one dynamic loading, right? I think last week, right? There's a serious earthquake in Taiwan. Right? Earthquake, we can analyze the behavior of structures under earthquake using the concept of structural dynamics. Displacement is not a constant; it's some like functions. So here, dynamic problem does not have a single solution. Normally, you can express them using a time series. Some example of dynamic loadings. I showed you one already. Sine loading, sine something, sine loading, sinusoidal force. It can be cosine, sine or cosine, depends on what function you would like to model the force. Normally, when the machine operates, it will generate up and down force, pushing the beam or slab under something like a sinusoidal force. When a ship, a propeller rotate, it will generate this kind of loading. Not a sine curve, but something like we call it periodic loading. You can find out one particular period. This is one period. You can use this repeated pattern to generate the whole loading history. For this kind of loading, we call it periodic loading. You can find out one repeating unit. Using this repeating unit, you can generate the whole loading. We call it periodic loading. This is the period. The period means the time to complete one vibration, one pattern. Periodic loading, and you have non-periodic loading. When there is explosion, say for example, when there is explosion, this explosion will generate a pulse. The pulse attack a building. The shape will be something like this. At the beginning, you have a very high loading, high pressure applied on the surface of the structures. And then the pressure will decrease with time. And based on some experimental study, we found that in some time region, it will under negative pressures due to explosions, blast loading, blast means explosion, blast pressure. They are non-periodic. Or earthquake. Under earthquake will make the ground under excitations. Ground excitations. The ground movement transmits to the structures, making the structures oscillate up and down, left and right, etc. Earthquake breaks. So dynamic is very general. You may also think in this way: static is only one special case of dynamic, in which the force does not change with time. So static is a very special scenario. Different loading give you different structural response. You may have different displacement. In the following chapter, in the following topics, topic 5, topic 6, topic 7, we are considering different loading effects. So there are different characteristics, right? We just talk about time effect. When you talk about dynamics, everything becomes time varying. The displacement, force, etc. They depends on time. The other important effect is that when you formulate dynamic equations in a dynamic problems, you will start to see the mass involved in your formulations. When you talk about dynamic problem, you need to consider something called inertial force. One classical example we have already introduced. When you write down the equation F equal to ma, mass appeared in the equations. In the past, when you consider static, you seldom put the mass in the formulation, right? Just like Simmons method. What we do in Simmons method, Q equal to KD, you never consider mass in the formulations. But when you formulate dynamic problem, mass involved in the calculations. This is the other thing you have to pay great attention. Mass, we call it inertia or inertial force. Mass time acceleration give you something like a force. Then what is inertia? Inertial force is you may call it something like a resistance. When an object start to move due to loading, there is some resistance prevent the object to move. This kind of resistance is called inertial effect. Okay, opposite to the acceleration produced today. This is the other effect. The first one is time varying. The second one is mass, the inertial effect. Some new characteristic we seldom considered before. This is the third one, the third characteristic. Energy dissipation. In the past, in static problem, we also do not have this phenomenon. What about energy dissipation? Let me think about this scenario. If you allow the structure display horizontally, say here you firstly pull a structures to the right, and then you release the conditions. The structure will oscillate back and forth. Right. These oscillations will not exist forever. Right? As time goes on, based on our common sense, we believe that the oscillation will decrease with time, just like the displacement graph as shown on the right. At the beginning, maybe you have a large oscillation amplitude, but as time goes on, the vibration amplitude decrease, finally converges to zero. One classical example is also a simple pendulum with a ball attached by a string to a wall, to a roof. If you, at the beginning, if you use your hand, put the ball right here at these positions, away from the equilibrium positions, and then you release the ball will oscillate back and forth about the equilibrium positions. But because of some effect, finally the ball will rest back to the vertical at rest positions. Right? Why the ball will go back to the undeformed positions? Because of this effect, energy dissipation. When the ball oscillates under air, it may have air resistance, right? It may also have the other energy loss like the friction at the joint, or you may have the other energy dissipation like sound. For structures, you have concrete will crack, or the steel material will yield. They will generate different kinds of energy loss. Energy will not always used to make the structure vibrate. Some energy will dissipate, lost to the surrounding. This explains why the vibration amplitude decrease, because you have fewer energy convert to KE, convert to PE. This effect is called energy dissipation. In dynamic system, you need to consider this energy loss effect in your formulations. Again, this one is never occurred in your static problem, because we can see that this energy loss is something related to time. In the past, we never considered time. But today, you need to know how to do a simple formulations. For engineering, we don't like complex formulation. So later you can see that you can formulate energy loss using some simple formula, not that difficult. But at least you need to bear in mind that we have some phenomena like this. We have time effect, time. You need to consider the mass, the inertia, and finally we have energy loss, energy effect. There are some terms here, free vibration, something like that. We will formally discuss free vibration in topic 5, the next topic. This graph are actually extract from the next notes, topic 5. Show you what is energy loss. So right now we have some brief discussion about the key characteristic of dynamic problems. Next, I would like to let you know how to formulate our equations. Right? After knowing some basic background, it's good to take a look how we can formulate a problem. It's also good to see the difference between static and dynamics. Why don't we start from our simple structures? Oh, I should cancel the S, sorry. Why don't we start from our simple structures? How simple? We consider a water tank. It's simple enough, right? We have a big mass at the top, and it is supported by some column at the bottom. I believe that it is very, very simple structures used to explain how to formulate equation for dynamic system. When you formulate a problem, we always need to make some simplification or assumptions. We call that structure idealizations. You have seen this term before. In where? In our introduction sections. In our introduction sections, we introduce structure idealizations. So, for example, for a beam, you need to assume that the beam is just like a straight line in your calculation, right? For support, you convert a support to either pin support, fixed support, or roller support. Right? This is also idealizations. You simplify one complex problem to something that you can handle. For dynamics, you also need to simplify the problems to something that you can formulate. When you read all the textbook, dynamic textbook, no matter which one, they always start from this ball and stick model. Okay, ball and stick model. What is it? This structure water tank has a big mass at the top. There is also mass for column, but as compared with the mass at the top, the column mass is negligible. So here at the beginning, we will assume that all the mass are concentrated at the top. All the mass are concentrated at the top of these structures. That's why you can put a big mass at the top with a value equal to m. Okay, you may call this lump mass assumption. Lump means concentrated. Lump mass assumption. This is a value used assumptions. Mass. Then what about the column? The column, we ignore their mass. We ignore the column mass. Okay, suppose we have maybe we have loadings, excited structures horizontally. Suppose we would like to excite structures horizontally under horizontal movement. The mass, what will happen? The mass will start to move horizontally, right? But the mass will not move continuously like a car, right? Because there are some support at the bottom, prevent the mass display horizontally, right? We call that stiffness. The column provide lateral stiffness to resist this motion. Stiffness, maybe you can use stiffness constant K. We have many columns. You find out the contribution of each column and add up all together. Then you can find the total stiffness provided by the column. Symbolically, stiffness, just like a spring. So here we use a spring to denote the stiffness component. We use a spring to denote the stiffness component. Just like here. This spring provides a horizontal stiffness. So when you excite the mass displayed horizontally under a dynamic force, the spring provides resistance against their motions, prevent their movements. Symbolically, we use our concentrated springs. This stiffness constant K depends on the column property. If you have many columns, if the column is strong, then you have a relatively large K. This is our simplifications. We assume that the column can be reset using a single spring, which considers all the effects of all columns to make the equation more easy to formulate. Later on, I will show you how to find out this K. I think in the next few slides. So this line, you know what is M. M just means the mass. You know what is K. K means the stiffness. Then what about the last item? C. C is something related to energy dissipations, the concept that we introduced on the previous slide. In a dynamic system, we need to model energy dissipations. You can think in this way: when this mass oscillates, this oscillation will not exist forever. this oscillation will finally disappear because of energy dissipations. Then how to capture energy dissipations in our formulations? In all the textbook, in all the structural dynamics theory, we normally use one so-called damper. We use a damper. We use a damper to model this energy dissipation property. Okay, this is a highly simplified modeling techniques, but at least it's work. So C is a damper. This is a damper. The green symbol is a damper. It's used to describe the energy dissipation property. We use a single constant to describe this energy dissipation property. We use a constant C. We call that damping coefficients. Damping coefficients. So when a structure displays horizontally, we have effect of mass, we have effect of stiffness, we have effect of damping, C. The mass will display horizontally by a value U. We use U to denote the displacement here. So this is a basic system in our dynamic problems. One mass, one stiffness, one damping, one displacement, one movement, right? We have one displacement here. We have only one displacement in our formulation on this page. According to the terminology that we learned before in Sylvus method, if you have only one displacement, 1 degree of freedom, then you can call this single degree of freedom system. The short form is SDOF. SDOF. This is our universal terms. So when you read the textbook, if you see SDOF, basically they are talking about the single degree of freedom system. When you read all the textbook, they always start from single degree of freedom system first. Show you some basic idea for its structural dynamics. SDOF. So in conclusion here, you can see that at the beginning, let us consider single degree of freedom system. To describe a single degree of freedom problems, you need 3 properties: M, mass; K, stiffness; damping coefficient, C. MCK. MCK. Remember that when you want to describe a single degree of freedom system, you need 3 parameters, MCK. This system is under some external force, the dynamic force. P, maybe I simply call this P. Okay, MCK. For static, in the past, you just consider K. But when you move to dynamics, there are 2 more parameters, M and C. This is single degree of freedom system. We start from here, okay? But in the future, we will extend this concept to multiple degree of freedom system. Think in this way. This water tank, just like our single story structures. This water tank, just like our single story structures. If you have multiple story structures, 2nd story, 3rd story, and so on, then you have more than 1 box on the top. This system is called multiple degree of freedom system. You will need to learn this concept later. MDOF system, multiple degree of freedom system. It's more realistic because for a tall building, you have multiple stories. Each story represented by 1 mass. Then it becomes this. Personally, I call this fishbowl model, just like a fishbowl. And yeah, let us have a look to see the formulations. Degree of freedoms. We learned this term in Sylvus method, so here just some review. One slight difference. In our Sylvus method, we describe our degrees of freedom at the node, right? At the node for Sylvus method. In structural dynamics, we normally assign degrees of freedom at the mass. A mass just like a log, actually, right? Just like a node. We describe degrees of freedom at location of the mass. In general, for our 3D problems, 1 mass, 1 node has totally 6 degrees of freedom. 6 degrees of freedom. Free translation, U1, U2, U3, it may translate horizontally, vertically, or this right direction. It may rotate about X, Y, and Z directions. Free translation, free rotation, just like Sylva's method. So you can see that our problem before here is highly simplified because you just consider one movement. But I think it's good enough to as a starting. At the beginning, it's not good to consider all degrees of freedom. It's quite difficult to do so. That's why we consider only one particular displacement to test the behavior of structural dynamics. We will express displacement using a simple U or X. Normally I use U. So let's have a look. Suppose we have a one-story structure with a slab on the top supported by two columns. Okay, we just like massless column. We ignore the mass of columns. Then what we are going to do, if you want to formulate this equation, these structures using a single degree of freedom system, we just use one single degree of freedom system, which means we only consider one particular U. Say, for example, we consider this horizontal movement due to wind load or due to the other effects. The other displacement are all equal to 0. That's why we call it single degree of freedom. Just consider one particular movement, one translational movement. Next, you can find out the total mass of the slab. If you know the volume, if you know the density, then you can calculate the mass of this slab. Put it at the top of these structures. And then you can see a more simplified picture, a 2D version. Right? When this mass displays horizontally, column will also bend under double curvature bending. Column provides stiffness in terms of their fractional rigidity, EIC. Beam also provides some rigidity, EIB. Beam and column provide stiffness. We mentioned that we can combine the effect of column. We can combine the effect provided by column. Combine the stiffness provided by column in terms of one single constant called K. We combine column effect into one single stiffness called K. K is the total stiffness provided by the two columns. For damping energy dissipations, we can use a simple damper to describe the energy dissipation mechanisms. So it's finally convert a real problem to something like a ball and stick model. Actually, single degree of freedom system means these simplifications. Only consider one movement. We group all the stiffness together into one terms. We use one single constant to describe energy dissipations. And when this system under movement, it will display horizontally. It may be a sine curve, or it may be cosine or arbitrary functions. So this is the idealized system. This single degree of freedom system is characterized by three properties: M, C, and K. MCK. Okay. I will let you know how to formulate their relationship in the next parts. But before that, I need to talk about some properties. Say, for example, maybe you feel strange how we can use a single stiffness to represent the stiffness provided by column. Or maybe you may think, hey, what is damping coefficients? So before moving on to the formulations, I would like to use a few slides to explain what is K, what is C, these kind of things. K is not a new thing. K talk about stiffness. We play with stiffness long time. Stiffness, where we can find stiffness? Firstly, we found stiffness in our Hooke's law. Hooke's law tells us force equal to stiffness time deformation, diffraction, something like that. F equal to Ku. U means displacement. Actually, it's just like a spring. It's just like a spring. In the past, when you learn Hooke's law, you learned that force equal to spring constant times the deformations. When you go back to the structures, when a structure is under one concentrated force, at best, the structure will display horizontally. And the resistance is provided by the column. So mathematically, column can be represented in terms of something like a spring. You just need to find out the corresponding stiffness. Then they will be equivalent mathematically. Then what is the stiffness provided by column? At the bottom, I showed you two scenarios. Scenario 1 and scenario 2. Scenario 1, if the slab or if the beam is fractionally rigid, if you consider rigid beam, rigid slab, rigid in bending. In this case, when column display horizontally, based on static analysis, we found that the stiffness provided by each column is equal to, I call this K column. The stiffness provided by each column is equal to 12 EIC. E is the elastic modulus, I is the moment of inertia of column over H cube. Based on static analysis, force displacement relationship, we can find that the stiffness is equal to 12 EI over H cube. Actually, you can find out this term from our stiffness matrix. One column gives you 12 EI over H cube. If you have two columns, then you multiply by 2. 3 columns by 3, and so on. That's why in general, you can add up all contributions together using summation notations. If you consider rigid beam assumption, you can find out K using these simple equations. Okay, K is not unknown. K is something related to column property, related to their elastic property, elastic modulus, related to their cross-sectional property, related to the height, the length of the column. So K is not unknown. K depends on the property of members, columns. The other thing is, if the slab is totally flexible, no rigidity, then you may calculate using a smaller factor, 3 EI over H cube. Actually, this one is derived from cantilever, just like a cantilever. You apply a force, find out the force displacement relationship. That becomes the Sylvus constant. You can do a static analysis of apply a force for a cantilever column, find out the displacement, delta, E equal to something times delta. You can do analysis, find out what is the expression for this bracket. This bracket is so called the stiffness. By analysis, it is equal to 3 EIC of H cube. Again, depends on how many columns you have in the structures. So you can find out K immediately if you know the column properties. I think when you take a look on these descriptions, you can see that these are two extreme scenarios. Rigid, totally flexible. You can see that it is two extreme scenarios. In reality, the stiffness should be somewhere in between, not totally rigid, not totally flexible. But we can't find out the exact number right at the middle. So normally in our analysis, we adopt either one of these two extreme assumptions. Normally we use rigid in my example, and then you can use this equation, find out the corresponding stiffness. Okay, this is the description about stiffness. Same as what you learned before, just like a spring constant. They're equivalent. But you can see one assumption on the right. The assumption is that this equation is true if you are talking about a linear system. If not linear, then this equation becomes wrong. Okay? So even though we are in dynamics, but we are still talking about linear. Damping is a totally new term to most of us. So here I use 2 slides to explain a little bit about damping. I explained already here. Use simple pendulum. If you allow a ball swing horizontally, finally the ball will rest at these vertical positions. When you draw these displacement diagrams, it will be something like this. The response at the beginning, very, very large, but the vibration amplitude decrease as time goes on. Right? This energy loss is so-called damping. Then why we have energy loss? Because we have different energy loss mechanisms. Here I give you some example. For building, it may lose energy due to temperature effect, due to internal friction between the joint or between the partition wall. Right. They are not. When the walls slide relatively to the boundary, then they are friction. Friction-induced energy loss. At the steel collection, bolt collection, for example, there is also frictions, which also induce energy loss. Reduce the KE, reduce the PE. Cracking of concrete induce energy loss as well. Or yielding of steel. Yielding of steel is also one energy loss mechanisms. Friction between structural and non-structural components, just like between the beam to the partition walls. When the walls lie between the beams, it will induce friction. Friction induce energy loss. So actually in the building, we have many energy dissipation mechanisms. Okay, more than five. So the problem is how to model so many energy dissipation into our equations. We just want to use one single constant, right? See, to describe the problems. But in fact, there are many energy dissipation mechanisms. So to make the equation more easy, we just use a single constant C to describe the energy loss property. How simple? This is the simple equation that we use. We assume that damping can be modeled using something so-called viscous damper. This is a highly simplified assumptions, okay? What is viscous damper? Viscous damper provide damping force, Fd. Fd, just like Hooke's law, Fd is linear proportional to U dot. U dot means du dt. What is du dt? Velocity. Viscous damper assumes that the damping force is linear proportional to velocity. The proportional constant is C. We call the damping coefficients. Then you may ask, hey, why use this equation? The answer is very simple. This formulation is simple. Okay, we use a simple model to describe damping. In reality, in actual structures, you have many mechanisms. Yes, we just mentioned before. But the problem is we have no way to model that complex mechanism. Right? You can't put friction, you can't put temperature, you can't put crack into a single equation. No way. So here is the only way we can model a simple building using a single constant C. This damping is called viscous damper. The damping force depends on the velocity through a constant C. Not exact, but in most of the case, we found that the answer is appropriate. So we keep using it. Damping coefficients, C. The symbol is this, graphically, we use this symbol to denote damper, a dashpot. Again, it is a linear system. Okay, so we have a little bit discussion about what is stiffness, what is damping. Damping is quite complicated. There are many mechanisms, but in the model, we just use one single constant to describe whole things. So finally, we go to our formulation. Newton's second law. Newton's second law, F equal to ma. What is F? F means summation force, external force minus internal force, equal to ma. We use Newton's second law to formulate our dynamic equations. F equal to ma. F can be represented using external force minus internal force. Just like the picture here. We have a single degree of freedom system described using MCK. This system is under one dynamic force, P. P is external force applied from outside. In this system, there should be some internal force to resist the motion. Although the them out is not equal to 0, but there should be some resistance against the motion. What resistance we have? Stiffness, prevent the motion. Energy loss is also some mechanism to prevent the motions. So here you can see that Fext, external force, equal to our applied loading P. Internal force involves two terms: our stiffness force and our damping force. Damping prevent motion, stiffness straightforward prevent the movements. So there are two internal forces. We have two internal forces, but their result is not equal to 0. The result is equal to ma, right? Because it starts to move. Right? We're talking about dynamics. Change the expression a little bit. Move Fs, move Fd to the right hand side of the equation. So it becomes this one: P equal to mu double dot plus Fd plus Fs. What is Fs? Hooke's law. On the previous page here, Fs equal to K times U. What is Fd? According to this viscous model, Fd equal to C times U dot. So I just do a simple substitution. This gives us our equation for dynamic problems. If you want to know the response of these structures under applied loadings, your task is to solve this equation. This equation described using three properties, M, C, and K. The inertial effect, damping effect, and stiffness effect. Three things. You can write this equation in the other form like this: P equal to M, you differentiate it with time twice, plus C U dt plus Ku. I think you have learned how to solve this equation before. Second order homogeneous differential equations. That's why you need to learn mathematics, right? Otherwise, you can't solve these problems. This one is non-homogeneous because the fourth term is not 0. Anyway, I will let you know how to do it. Okay, don't worry. Not much mathematics involved. I will show you the standard outcome. Okay. In topic 2, in topic 5, we will consider free vibration. In topic 6, we will consider force vibration. Basically, I would let you know under different forces and how to solve it. I will let you know the solutions, corresponding solutions. Don't worry about the mathematics. And what I want to mention is that actually you are asked to solve this equation. Find out U. Find out what is the displacement. If you know displacement, then you know what happened for the structures. You can also evaluate the shear moment, etc. Okay, these are the things I want to mention using second law. At least maybe I wrap up the contents a little bit. Today we mentioned something related to dynamics right here. And we mentioned that for a dynamic system, at the beginning you can model using a single degree of freedom property. Single freedom system. For a single degree of freedom system is characterized by three properties, M, C, K. Their relationship is this one. P equal to mu double dot plus cu dot plus Ku. This is the equation that we need to use in the first part of our dynamic sections. This equation is called equation of motion. Equation of motion. Sometimes I call this UM for short. Next time I will let you know how to deal with these problems. Okay, don't worry, not much mathematics. Okay, these are the things I want to share with you today. Today we finish all the things within, we finish all the contents for Sylvus method, and then we enter a new chapter, dynamics. We start explaining a little bit about the formulations. Next time we will try to handle different scenarios. Let's see if you have any questions. If no, that will be the end of this class. Thank you for joining these sections. If there's no further questions, then I will close.